Good morning, ladies and gentlemen. Welcome to the Millennial Talks 3, with the theme is Pathway to Opportunity for Future Battery Technology. My name is Sinta Widiningrum, and I'm a secretary of the National Battery Research Institute, and it is an honor for me to be here as the master of ceremony for today's event. So NBRI is Indonesia's independent institute for electrochemical energy storage, science and technology, supporting research, training, and also educations. NBRI aims to contribute to the overall research capacity and training environment in Indonesia, especially in battery research. Today, we are here to discuss together with an expert who is actually still young, to share their knowledge and also experience in the sector of the future battery technology. Batteries are being used alongside other emerging technologies in areas such as renewable energy or AI and EV. Research is underway into how batteries can be used to share energy, to balance out the intermittent output, and to transform expectations of what's possible in the future. Through this webinar, with the topic of Pathway to Opportunity for Future Battery Technology, we hope to bring an insightful discussions of battery technology in various areas, including materials, component, device, application, etc. We hope to provide an understanding for millennials to get involved in the battery research to make a better global future by using green energy. So today, before we start the event, I would like to read the webinar rules for today's event. First of all, the participants are expected to follow the directions from the committee. Please mute your microphone, turn on your camera, and use a virtual background attached to you via email during the webinar. If you have any questions, please write down your question in the chat box or use raise hand feature during the Q&A sessions. Attendance form will be shared by the committee, and e-certificate will be issued to participants who filled in the attendance form. Participants who cannot join by Zoom meeting are welcome to watch the recorded webinar through YouTube channel of the National Battery Research Institute. So I will give a brief summary for what we're gonna discuss on this event. First of all, we will listen to the opening remarks by the founder of the NBRI, Professor Dr. Renat Evi Kartini, continued by the first discussions from Dr. Nur Ika Puji Ayu, Bachelor of Technique, with the topic of hydride ion conductor, and then continued by Mr. Dimas Yuniato Putro, Bachelor of Engineering, MBA, with the discussion of zinc ion battery, and then continued, last but not least, from Mrs. Fredina Distiorini, Bachelor of Science, Master of Technique, with Indonesian biomass waste for lithium-ion battery anodes, and then continued by Q&A sessions. Without further ado, we would like now proceed to the first agenda of today's event to start the event. So this is an opening remarks from our founder of the National Battery Research Institute, Professor Dr. Renat Evi Kartini. To Professor Evi Kartini, the time is all yours.
Good morning, everybody. Good morning, Sinta. Good morning, all the speakers, Fredina, Dimas, and also Ms. Ayu, yeah? Okay, yeah, and all the participants here. It is my great pleasure to be here in front of young researchers, students for the Millennial Talks, NBRI Millennial Talks. As Sinta said, that NBRI, it's an independent institute that we want to help to contribute for Indonesia, so Indonesia can be independent in energy. Yeah, this is very important. Independent in energy because we are rich in local resources. And the second, not only rich with the local resources, we need also to know, to understand the technology. Okay, the way to success, we have the resources, but we have also the technology. So all of you young scientists, yes, students have to learn, yeah, from all over the sources, from abroad, from anywhere, from industry, to have this key of the technology. But not the most important is the human resources. Okay, without the human resources, we are unable, yeah, to make Indonesia independent. So you are very, very important. Okay, before that, Sinta, can I share screen? Yeah.
Yes, please.
Okay, maybe you already see from our company profile before. I would like to introduce briefly what is the National Battery Research Institute. Yeah, so if you see here, the establishment of the NBRI supported by the Queen Mary University of London. Yeah, so at the beginning of the NBRI, we had the fund from the Global Challenge Fund. And for that, Professor Alan Drew become our co-founder. Yeah. So here you see that this is our team. Yeah, there is Mbak Sinta. Yeah, there's Mas Adit as the program director, as the finance director. Mas Firman as the program director, and Prof Alan, yeah, as the leader. Yeah, and also co-founder of the National Battery Research Institute. And we have all the millennial teams here. Yeah, also you welcome. Okay. Yeah, Mrs. Fredina, you are welcome also to join. Okay. Yeah, I mean, as a researcher, because this is independent, and all of you. Okay, Miss Ayu, if you come back, and also Dimas, please join. Yeah, to this is a kind rather different. Yeah, different from normal research because we start the research from the industry. What the problem and anything. So we have to make the acceleration. So we have here Mas Wahyu here. Yeah, Mas Wahyu is the assistant manager for the training. Mas Rido for the testing. Yeah, and Mas Subhan, corporate engagement. We have Mr. Fahrudin, assistant manager of research development innovation, and Safira as a creative and design. Yeah, and then currently we have the intern student. Yeah, that he got the award as the winner of our youth idea competition, Dinandra. Yeah, so become your moderator. Yeah, so we gave a challenge to opportunity to Dinan to have the internship in NBRI. Yeah, so he passed the selection actually. Yeah. Okay, so it's been mentioned before that this is the aim to contribute the overall research capacity training environment in Indonesia in battery research. Yeah, we want to bring not only the scientists, yeah, but scientists, industry, yeah, partner, yeah, to reduce the battery cost. This is still the problem. The problem of the battery is the cost. Yeah, this is one. So we have to find not the source that not imported. Yeah, we have to develop in Indonesia, so the price can be reduced. Yeah, and also maybe one example, I use the biomass. That is also can reduce. Yeah, I think you will hear later on. Yeah, so of course we have to improve the performance and develop the technology, and also the recycling is very important. Yeah. So this is the mission, yeah, together, yeah, same. We have the mission, put all the stakeholders together, yeah. And then our here mission also, yeah, to help develop battery manufacture industry using local resource, yeah. Help Indonesia, yeah, to be independent, yeah. This is very important. This is our platform, yeah, from the Research Institute. This is very important, yeah. Always the innovation come from the Research Institute, and then there is, of course, intellectual property, industrialization. We have to make the platform, but this is the most important. Normally, we do the research, but whether it be used or not for the what is the industry, sometimes but we have to start from what they have the problem, and then we do the research. Yeah, so this is a kind of approximation, approaching the different approach. Yeah, what NBRI do. Yeah. Okay, we have several milestones here. First, we already have this testing laboratory. Yeah, we start with the standardization. We have NBRI has been ISO for 14,001. 45,001 and 9,001. Yeah, I think during 1 year, and we have the collaboration international. Yeah, at the beginning already international collaboration, and we have we hope that can bring up the university and also the manufacturer. So this is our activity for the past year. We have more than 200 activity. Yeah. Webinar discussion and etc. Yeah, even 2 days ago we have also the Kartini webinar. Yeah, talk about the transition and women. Yeah, and then normally the participant coming from not only from Indonesia. Yeah, today also we have from various country. Five country. Yeah, I think so. We have partnership. This is the highlight. Yeah, we have the annual. I will tell you later. Yeah, an annual event, international conference, international school. Yeah, international workshop. Beside the talk. And then this is the activity. Yeah, we offer also the education and training that interns for the student. Of course, after pass the selection. Yeah. So this is several students that already have the training with us. Within 3 months, I don't know, KP itu, what is the KP? Just the project, but they can publish at least the proceeding, international proceeding. So that's one requirement with us, and I believe that you can do it within 3 months. Okay, 3-month publication. Okay, yeah, this is the participant, more than 35 country, and then this example of the activity. Yeah. Starting from design the materials, and of course we have from laboratory to pilot scale. Yeah, we have the pilot plan for the producing the cathode material. Yeah, for the NMC. So this is all the facility we have. Yeah, you can do the material preparation, battery testing. Yeah, and also assembly until the application. Yeah. There are various depending on your subject. Yeah, but this is for example from the UNPAD. I think she did the graphene from rice husk. Now it's being continued by Dinan. Yeah, in the other one made the NMC, and then a student from for example from electro. Yeah, we asked them to convert the bicycle, and they succeeded. Yeah, within six weeks. So I think this is all that we have. We have also the training syllabus, yeah, for the industry or for corporate. And finally, today we are proudly present the Millennial Talks, Pathway to Opportunity for Future Battery Technology. I'm great to have Dr. Nur Ika Puji Ayu ST. I think previously my student she did a thesis with with me. I have forgot which year. I think maybe more than 5 years ago, and then attended our conference, international conference, and then at that time she got promoted. Yeah, because the so readiness and others, students we over, to have the interact with the international speakers and to promote yourself, and then so they will invite you to attend. And Dimas, I met him. I already met him in conference in Australia. I think a great young scientist. And I think we had also last time talk at UNS. Yeah, I think, yeah. He can share also about how study in Korea. And then also Fredina, yeah, I think she's very talented, yeah. So she got the research prize from British Council for the Climate Challenge workshop. I think, yeah, all the speakers, I think great and young, yeah. So that's what made me happy. And then Dinan, as I mentioned, he won also the prize of Youth ID competition. Okay, before I end this, I want to show that the participation of this, that you see, well, this is millennial, so this is proposed for the student. Yeah, so 36% student, and then so many institutions attended, you see, yeah. I cannot read one by one, but so many, okay. And also there are students. And you see, you have the participant from UK, yeah, from Germany, and then India, well, Tanzania, so many. And then the participant age are mostly 18 to 25 years old that are millennial, yeah, and 26, 35 years old also still millennial, yeah. So for me, yeah. So I will propose, and then, yeah, this is the country. Okay, let's the final, please check the agenda. We have the conference that in June. So we already have the confirmation. Later on, Mas Wahyu will introduce you about this. A confirmation from the Battery Consortium USA, Europe, and Australia, and other speaker. Yeah, we have maybe more than 10 countries attended this conference. And then don't forget to have yes idea competition. Later on will be. Okay, thank you. Good luck for today's, and then I will give you back to Sinta.
All right, thank you so much, Prof. Evie, for such a very motivated introductions of NBRI. And as Prof. Evie mentioned before, that NBRI is also accepted by millennials, and all of us in the NBRI mostly are millennials. So without further ado, I will proceed to the next agenda. This event will be moderated not by me, but by our amazing team, which is Adinanda Cesar Fahrudin, Bachelor of Science. So before he took the place to moderate this event, I would like to introduce him. Adinanda Cesar Fahrudin, Bachelor of Science, is graduated in Physics from University of Gadjah Mada, Yogyakarta, Indonesia. And then he is a laboratory assistant in Department of Physics on 2020, University of Gadjah Mada, Indonesia, research assistant in Department of Physics 2020 to 2021, research group of material for battery and supercapacitor, University of Gadjah Mada, Yogyakarta. And now he is a research assistant intern on the NBRI from 2022 until present. So without further ado, I'll give the floor to our amazing team, Mr. Dinan. To Mr. Dinan, the time is all yours.
Okay. Thank you to Ms. Sinta for introducing me as a moderator for today's webinar. Allow me to take over the next session, starting with presentation by the speakers until the Q&A session. Next, please. Okay. Batteries are being used alongside other emerging technologies, such as renewable energy and electric vehicles. In today's webinar, we have three distinguished speakers from different countries, including Japan, South Korea, and also Indonesia. Let me first say hello to our speakers today. Hello to Dr. Ayu, Mr. Dimas, and Ms. Fedina.
Yeah, hello.
Okay. Thank you. I hope all of you are well and always in good condition. Thank you for taking your valuable time this weekend to provide insightful knowledge and experience to all of us. Next, please. For the first speaker, we will present Dr. Nur Ika Puji Ayu, ST, to give a presentation entitled Hybrid Ion Conductor. But first, let me introduce her CV. Dr. Ayu got his bachelor's degree in engineering physics from ITS in Surabaya, Indonesia, and she continues her doctoral studies in material structure science from Sokendai in Kanagawa, Japan. But she did his research in the Materials and Life Science Experimental Facility from G-Park in Ibaraki, Japan. She also had the opportunity as a research student at the Institute of Molecular Science from NINS in Tokyo, Japan, and won the School of High Energy Accelerator Science Teams Award 2021. Now, she is a postdoctoral researcher at the Tokyo Institute of Technology in Japan. Without further ado, please welcome Dr. Nur Ika Puji Ayu, Bachelor of Engineering. You have 20 minutes to deliver your presentation.
Thank you very much for the introduction. I will start to share my screen. I'm sorry, I think I have a little bit problem here. So please give me a moment. Okay, done. Yeah. Mr. Dinan, could you please confirm that my screen is appear?
Yes,
Okay.
please.
Okay, thank you very much. Then I will start my presentation. And is my voice is clear?
Of course.
Okay, that's good. Okay, thank you very much. Okay, good morning, everyone. Thank you very much, especially for Professor Evi Kartini and also NBRI team for giving me this opportunity to share my research experiences in Japan. So we know that when we talk about the rechargeable battery, lithium is one of the most famous and commercial battery, but I want to share other carrier today. So I will deliver presentation about the current report on hydride ion conductors. Sorry. Okay. My name is Nur Ika Puji Ayu. I'm a postdoctoral researcher at All Solid State Battery Laboratory, supervised by Professor Ryoji Kano at Tokyo Tech. And my research topic is the hydride ion conductor study and exploration. I mainly did experimental, but since I work at the Tokyo Tech, I start the calculation study because we have supercomputer at Tokyo Tech. And I did postdoctoral, I did doctoral study at High Energy Accelerator Science, supervised by Professor Takashi Kamiyama in collaboration with the National Institute of Natural Science, supervised by Associate Professor Genki Kobayashi. And before I came to Japan, I spent some time as work as research assistant under supervision of the Professor Evi Kartini. It was at 2015, yes, before I came to Japan. Okay, so basically the outline of my presentation. First, I want to share about the hydride ion conductor, and then the second, maybe a little bit experience of research at KK. To the a bit sharing about my research at KK J-Park, maybe more like my self impression or such kind of thing. So J-Park is one of the world-class neutron facility. Actually, there are I think around 10 neutron facility in Japan. But the J-Park in Ibaraki is one of the biggest, not the biggest, the biggest facility in Japan. It's located in Ibaraki Prefecture here in KK Park. And this is the real site, the site. So you can imagine it's so huge facility. And for the neutron experiment, I usually performed at the Material and Life Science Experimental Facility shown in this figure. And then here is the appearance of the experimental hall. So actually the experimental hall is full of instrument, like, yeah, it's I call it like a playground. And then we have several neutron beam instrument. So actually the neutron was produced by the injecting the proton beam to the target. Here we have the liquid HG, the neutron target, and this is the real size of the neutron target. The real size, and yeah, this is the real target. They just replaced and they kept the old one as exhibition. And basically I perform, actually there are many beamline, there are several maybe several beamline, but I basically work with Spica BL09, which is one of the dedicated beamline for battery study. We can perform in situ charge, discharge, and also power diffraction. And other thing is we want to customize, we can just discuss with the beamline scientists. Okay, yeah, maybe some of the researcher will have interest to perform the neutron experiment. Thank you very much. Here I show my picture. I've been moving within 3 different groups in Japan. From Kobayashi group, I learned about the solid electrolyte, about the synthesis, about the experimental part of the battery, hydride ion battery. And then from Kamiyama group, I learned about the neutron, the fundamental of neutron, and the like experimentally and theoretically. And finally, in the Kano Suzuki group, I learned about the solid state battery, how we design, how we explore the material, and also I got an opportunity to learn about the simulation study. So for the exploration, usually we calculate the material, whether it is stable or not, and whether the material will have high conductivity or not. If the material is worth it, then we will do in the lab, and it's quite save a lot of time, I think. Thank you very much. That's all from me. I will return it to the Mr. Dinan.
Arigato gozaimasu. Thank you to Dr. Ayu for your kindly presentation. Actually, you still have 2 minutes left, but it's okay. We will continue to the next speaker. To all participants,
Thank you, Ayu. It's great.
To all participants, I'll remind you that the Q&A session will be open after the presentation from the third speaker. Please write down your question in the chat box or wait for the Q&A session to ask your question directly to the speaker. The next agenda, we will present our second speaker, Mr. Dimas Yunianto Putro, ST MBA, to give a presentation entitled Zinc Ion Battery. Please allow me to read his CV. Mr. Dimas got his bachelor's degree in metallurgical and materials engineering from the University of Indonesia. He also has a master's degree in business administration from Guglielmo Marconi University in Rome, Italy. For her PhD, he studies material science and engineering at Chonnam National University in Gwangju, South Korea. He is also a battery researcher in Nano Energy Lab at the same university. Now, he is a senior consultant at 9 Sigma in Tokyo, Japan, and had nominated as a platinum member of Senior Industry Expert 2020 by Open Innovation Council in Japan. Okay, please welcome Dimas Yunianto Putro, Bachelor of Engineering, MBA. You have 20 minutes to deliver your presentation. The time is yours.
Okay, thank you, Dinan, for the time and introduction. And good morning, good afternoon, ladies and gentlemen. Okay, I will share my screen. Thank you for Prof. Evi for the invitation to be speaker in this forum. And thank you for the NBRI team to invite me.
Thank you, Dimas, for your acceptance.
Okay, Prof. Yeah, thank you so much also. Yeah, today I'm going to present my research in Korea. So now I'm a final year student in Chungnam National University in Gwangju City. It's about maybe 3 hours from Seoul, go to the southern part. So here in my lab, the name of the lab is Nano Energy Lab. So we are doing the research in battery. So not only lithium battery, we also doing the sodium, potassium, and also zinc battery. And then I'm in zinc ion battery group research. Okay. So as we know nowadays, lithium ion battery is very important part of our life. Sorry. We are using many of this technology in our mobile phone or our laptop, and now being in the car or a bus, and maybe it will be in our airplane in the few years, in the future years. So as we know here, the lithium ion battery technology is come from the mining activity. So there is like company here for the mining, and then there is chemical converter also doing the business and development in this lithium ion battery technology. And we have this cathode and anode producer for the electrode, for the positive and negative electrode. We have this one Umicore in Europe and some like Cattle in China for the producer. And in Korea, we have like LG Chemical, or now they change into LG Energy Solution for making the battery, and Samsung SDI. And also from Japan, it's Panasonic. And the car makers, as we know, Tesla is leading company to make the electric car, and the others is like BMW and Volkswagen from Europe. So we in our lab, we always do like updating our technology and research method. As we know here, in this battery technology, we have R&D, research and development. We are doing the optimization and standard process here. And then after we finish our R&D, we have done, we go to next step to make a prototype. So I'm also in my lab do some prototype to make pouch cell to make the zinc ion battery, and then yeah, it's success from prototype. We scale up with the technological update and market research also to make this business going through, and then manufacturing process after the scale up for make the final product and production growth. So as you can see here on the right up of the graph, we need a lot of lithium to make the rechargeable battery for our electronic device, and then graphite as anode materials, and cobalt, nickel for the positive materials or cathode materials, also some rare earth inside. And then when we can see here, the China is the leading production for the rechargeable battery for the lithium, and then the second is Chile. So actually Chile is the place for the natural resource for the make the cathode or anode material, and the other like Argentina, USA, they have cobalt and nickels also. Okay, next. So what's the zinc ion battery actually? This is the main part of my presentation. This is the introduction of the zinc ion battery. So as we know, lithium ion battery is very popular nowadays, but it's getting very expensive, right? So we need to have another materials to keep running our computer, our laptop, our phone, or our cars. So why zinc chemistry can solve the lithium, can replace the lithium-ion battery technology. So zinc is 100 times more abundant and cheaper than lithium. We can find many zinc natural resource in like Bangka Belitung or in Sumbawa. They have also there the zinc resource, but not many people use the zinc, especially for the battery technology. And then this previous zinc chemistry have struggled to deliver on power, size, and rechargeability. But we accomplish this by developing new materials that can absorb zinc ions in a process called intercalation. So this is like the process is intercalation, zinc ion intercalation to the cathode, and then go to take out from the cathode, go out to electrolyte. So importantly, this enables the use of mild electrolyte that allows the battery to be recharged thousands of times. The second reason is 100% compatible manufacturing. So by using the same fundamental principle and design as lithium ion, every time lithium ion batteries can get cheaper to produce. So does zinc ion. This makes it far easier to scale up zinc ion production. So actually, when we assemble this zinc ion battery, we don't need glove box. We can just assemble like in this atmosphere place. So actually, because the zinc is not oxidized in the common atmosphere, so we don't need argon gas inside the glove box, or like the electrolyte. Also, we use the DI water, like water-based electrolyte. So we put some like the zinc sulfate or manganese sulfate to make the electrolyte. And then the third reason is safe and non-toxic materials, as I said before, because the electrolyte is water-based. So zinc ion water-based design is completely fireproof. So will not explode or make fire when it gets short circuit. Our fireproof design reduce costs, simplifies installation, and avoid complicated regulatory hurdles. In addition, the zinc ion chemistry avoid the use of toxic materials, which further increase safety and recyclability. So it's very safe for our environment, and then will not toxic when we like throw to our environment, not like the LiPF6 as lithium ion electrolyte. And then the last is ready to transform the grid. So actually, this zinc ion is for the energy storage system. For the we can use like for the renewable energy storage to like store from the like solar cell or wind power plant, like that. So a grid that runs primarily on the wind and the sun needs batteries to work. So to save the energy during nighttime or during the noontime, lithium ion is the best solution available, but in addition to its safety and supply chain issues, it is still far too expensive to enable to clean electrical system. So we made to save an inexpensive battery that can directly replace lithium ion to help power the clean energy revolution. So the main purpose of the zinc ion battery, because the weight is not as small like lithium ion battery, so we can use this zinc ion battery as energy storage system to put in a grid as a smart grid for the renewable energy power plant. Okay, because maybe some of the audience just know about the zinc ion battery. So actually, this zinc ion battery system already like produced in Canada and some Europe countries. So in 2018, from 2018 until 2025, there are like a lot of company. Here I put non-energy. They develop zinc air batteries, and then this zinc aqua system. They produce this company. This company is, as I know, it's from Canada. and then they make the zinc ion battery ecosystem for the energy storage system. And then the other company make zinc solid state electrolyte to produce more reliable technology for this zinc ion battery. So how about the market entry and other market projection for the future? So for the market entry, this technology has low cost backup and microgrids. And for the market growth, it's different grid upgrades. So not only lithium, we can replace the energy storage system for the power plant with this zinc ion battery, and it's starting to mass market capture. So with the ultra low cost mobility, it can give solution for the lithium ion battery energy storage. And this ZIB or zinc ion battery is getting more attention for energy diversification to compete with lithium ion battery cost and environmentally friendly. So we are not going to replace all lithium ion battery technology from the phone or cars and laptop, but this zinc ion battery system is for the diversification to produce for like energy storage system from solar power plant or wind power plant and etc. all for the renewable energy. So here, design from the atom up to transform the grid is actually very challenging. So the first is tailored for the stationary. In this step, we optimize for lifetime cost and safety. Zinc ion is perfect when weight doesn't matter. That's why I said it's for the energy storage system, smart grid system, for the renewable energy storage. And then the standard manufacturing is this ZIB is easy to scale since it can build using standard lithium ion process and equipment. So there is no new process and can I say manufacturing. So we can just replace the zinc, the lithium electrode with the zinc electrode to make this zinc ion battery can work. And no risk of fire. This 100% safe, can eliminate the need of fire protection system. So because of the electrolyte is based on water, not the organic electrolyte that very easily to catch the fire, when it's get short circuit, it will just die. There is no like explode or fire fire attention. Okay. So we talk about the market growth for this zinc ion battery. The development for this battery market from 2005 to 2030 actually grow very growth much from 2005. As we can see here, the annual cell energy demand is growing up. So in 2030, we predict 1,500 of the demand of all the rechargeable battery. And then for the microgrid capacity also, it will always increase in the future till 2026. So not only for the battery, but solar, fuel cell, diesel technology, and then hydro, wind, all the energy that we need in the future for our daily life, it will get increased. And then here, mass production of the zinc ion battery is already on the progress. Salian company, they made the pouch cell of zinc ion battery, as you can see here. This is the pouch cell is just like lithium ion battery pouch cell. So we use the cathode like manganese oxide or vanadium oxide, and then for the half cell, usually in our lab we use the zinc metal. And then the other company, Nantech, like this, they already make this energy storage microgrids for the power plant, and then this a lot cheaper than lithium-ion battery. It can be 6 to 10 times cheaper than lithium-ion battery. And then for the zinc-ion battery, we need also smart energy management software to predict and then to control the life cycle of the battery. It's just similar like lithium-ion battery. Okay, so I share this. Oh, sorry. I share my lab research and development, and then we publish some papers for the zinc-ion battery. The first experiment that I show here, but it's not the first that we have done. This is the good one for the example for the orthorhombic KVO. This is as a cathode material, the KVO. So we use this cathode material for the zinc-ion battery, and it can reach until 1,500 cycles with the capacity about 150 milliampere per gram. So as you can see here, the system is like intercalation, and then this is the materials is layer structure. So it's easy for zinc-ion. Zinc is 2+, not like lithium. Lithium is 1+. So it goes in and goes and go out from the cathode, and because it's layer structure, so it's easy to for the zinc-ion to go in and go out. And then for the second papers, we have here with the NVP for the cathode material also for the zinc-ion battery. It can reach until 100 cycle at this time, and then there is no peak for the no peaks corresponding to possible zinc inserted. No peaks corresponding to possible zinc inserted phase. So it's owing to zinc 2+ has slower kinetic than the sodium plus. So that's why it's not going that much. For the capacity here, it's about maybe 82, 85 milliampere hour per gram for the first cycle. But this is breakthrough research, because it can eager for other researcher to develop another structure for this material. And then this material structure has tunnel structure. Also zinc-ion battery can go in and go out from the tunnel structure. And then the next, we finish with the vanadium base, and then also the battery can work from manganese base materials. Oh, sorry, is it the time is?
No, you have 4 minutes left.
4 minutes left, okay.
Okay.
Yeah, enough. And then we develop another materials for zinc MNO with the carbon coating. It can reach until 2,000 cycle for this battery system, and then we already try with the coin cell, and then it can work for the digital clock. And then this is the last for my research, my own research. We published in Electrochemica Acta, and then I use this zinc-ion battery with manganese oxide cathode, but the electrolyte is gel. So it's from the porcine skin or pork skin. The gelatin is from the porcine skin. We can use this battery without any close packaging. So we can just put the cathode and then the anode here, and then with this gel electrolyte, it can work for the battery. After 1 month, it still can work like this in E figures, and it can reach until 100 cycle for this life. Then this is how I made the electrolyte. Okay, so that's all for my research as zinc-ion battery researcher in Korea. So maybe I'm gonna share a little bit about scholarship in Korea. Okay, so usually people who do the master or PhD degree here, they got a lot of scholarship from different and many kind of scholarship that you can get from Korea or from Indonesia. The first is LPDP scholarship, as you know, it's from the Ministry of Finance, and then it can enter some universities, top universities in Korea, like SNU, TAIS, this SNU in Seoul, and then it can cover your living costs this much. And then the second is Global Korea Scholarship. It's from the Korea Government Scholarship. And then it's from the degree from master, from bachelor to doctoral degree. And then the third is KAIS Scholarship. This is the best engineering institute or university in Korea. They also give the scholarship for the bachelor degree program. The fourth is POSCO Foundation. This POSCO is steel company, metal steel company in Korea, and then in Indonesia also they do merger with the Krakatau. That's why they give also the scholarship for the social science or engineering in Korea. It's for the master and doctoral degree. The fifth is the research scholarship, or from the UST or University of Science and Technology in Korea. So yeah, this institute only give for the master and doctoral degree, and then they don't have the bachelor program for this for their institute. And then the last is professor scholarship. This is the scholarship that I got. So we can just contact the professor in the Korean university, and then when they open for the student, and we can just apply or contact by email. And then the salary is very huge range. It's from 1.3 million to 2.3 million or 2.5 million in some labs. So it's more than enough for your life in Korea to get this much per month. Okay, thank you for the time. Dinan, I give back to you.
Okay. Thank you to Mr. Rimas for your interesting information. We will continue with the third speaker before getting into the Q&A session. Participants are allowed.
Yes.
Participants are allowed to ask questions either in English or in Bahasa Indonesia. Please write down your question in the chat box for now. Our third and last speaker for today's webinar will be Ms. Fredina Destiorini, SSEMT. She will give a presentation entitled Indonesian Biomass Waste for Lithium-ion Battery Anodes. Before we hear her presentation, let me introduce her CV. Ms. Fredina got his bachelor's degree in physics from Airlangga University in Surabaya, Indonesia. Then she continues her master's degree in materials engineering from the University of Indonesia. Now she received GSPS Ron Paku dissertation PhD fellows from Osaka University in Japan. She has been working as a researcher in Research Center for Physics, LIPI, for almost 13 years. Now, she is a researcher in Research Center for Advanced Materials, BRIN, in Indonesia. She is also the first winner of the Research Prize in the Climate Challenge Workshop in 2021, held by the British Council and NBRI. She already has 15 international publications, 8 national publications, and 11 patents. Without further ado, please welcome Ms. Fredina Destiorini. You also have 20 minutes to deliver your presentation. Thank you.
Thank you, Mr. Dinan, for your introduction. Allow me to share my own screen. Mr. Dinan, could you see my slide in your screen?
Yes, very good.
Okay. Thank you. Good morning, everyone, all Millennial Talks participants today. First of all, I would like to say thank you for NBRI, especially Prof. Evi Kartini for inviting me to this event. Thank you, Prof, to share a few of my research experience in the battery field. In this time, I would like to share about Indonesian biomass waste for lithium-ion battery anodes, and also my experience on research prize winner. Okay, this is my presentation outline today. I will start from my experience on research prize winner of climate challenge workshop, then continue to sharing about research experience in the battery field. Okay, allow me to start sharing my experience in on research prize winner. Okay, for me personally, NBRI gave me a great experience, particularly at the Climate Challenge Workshop event, which was held in July last year in collaboration with the Queen Mary University of London. This event was funded by British Council with total price of around 30,000 pounds sterling, with the theme Delivering Battery Revolution, Reducing the Driver of Climate Change in Indonesia. This workshop provides 4 programs. There are research prize, dissemination awards, lecture, and the breakout session. This program specifically aimed for early career researchers from Indonesia and UK, and I participated in the research prize program with prize up to 8,000 pounds sterling for conducting research involving battery, climate change, and Indonesia. And in this event, research prize participants should pass several stages of selection, which include administration selection, and the second, we have to pass twice a networking event, first and second networking event. In this networking event, the selected candidates were invited to an online discussion, even to build relationship between candidates and find partner. We also gave presentation regarding our research plan in simple slide. We also received briefing from mentors on how to prepare our proposal, and they are our mentors, Prof. Colin and Prof. Tanner from Queen Mary University of London. We also have Prof. Edwin from BRIN and Prof. Anna from University of Indonesia. From them, as well as Prof. Alan and Prof. Effie, we received valuable insight to prepare our proposal and determine our research target. They are in line with those expected from this event. And the last stage is final presentation. In this stage, the selected candidates presented our research plan in full version in front of the mentors and judges based on the proposal that we submitted. And after going through the selection, the winner will be announced on the last day of workshop. The 3 best winners have received a prize of 8,000 pounds sterling to carry out the presented research. And on last February and March, we had to give our progress and final report to NBRI in the presence of Prof. Alan and Prof. Effie as chair and co-chair. We report about the problems were met and what output were successfully produced. So there is the experience that I can share related to my participant in Climate Challenge Workshop event held by NBRI last year. And I know now I will share about the research that I did related to the battery, and I submitted to this event. So my team and I proposed this topic, Indonesian biomass waste for lithium-ion battery anode. And this is a short introduction about why this project was proposed. Our climate change, which is global issue that is believed to be potential serious threat to the global environment, and Indonesia is both victim and source of climate change. Indonesia is the world's 5th greatest producer of CO2 gases, and on the other side, Indonesia will be a significant victim of this climate change. Impact all economic sector, and agriculture is often the hardest affected. Change in rainfall pattern may drastically reduce paddy and rice production and could impact the country food security. Therefore, Indonesia has to take up the challenge and taking action to reduce greenhouse gas emission. According to Indonesia climate pledge submitted to the Paris Climate Conference, target about 29 to 41% reduction in emission by 2030. In order to contribute in achieving emission reduction target, we propose to utilize the Indonesian biomass waste by converting it into material for energy storage device. In general, these are our purpose of this research. And this is our research design. Material for battery anode are generally used graphite material that produced from fossil fuels such as petroleum coke. The use of fossil fuel source to obtain graphite can increase CO2 emission and need very high temperature and high production costs, and also raise concern about sustainability and availability. And non-renewable fossil fuel derived graphite anode can be replaced by biomass-based carbon source that further treat and convert into a porous graphitic carbon. And Indonesia is blessed with abundant natural resources which are environmentally friendly, and coconut is one of the agriculture product of Indonesia. As the top coconut producing country in the world, Indonesia contribute about 30% of world coconut production. However, this great industry produce a large amount of agricultural waste such as coconut fiber, and it requires proper waste management rather than burning to avoid environmental pollution. And as a lignocellulosic material, coconut fiber is generally composed of cellulose, lignin, and hemicellulose, which at certain temperature will decompose into carbon-rich charcoal. So coconut fiber is renewable and sustainable carbon source. In this project, we carry out an effort in utilization the abundant and underutilized biomass waste, in this case, coconut fiber, into a value-added product, namely porous graphitic carbon, as anode material for lithium-ion battery, replacing the fossil fuel-derived graphite. And below is our experimental detail consisting two steps. At first step, we utilize the biomass waste, coconut fiber, as renewable carbon source. The raw coconut fiber was carbonized at 500 degrees Celsius for an hour under nitrogen atmosphere to obtain the amorphous of biochar. And then we the obtained biochar activated and graphitized at around 1,200 degrees Celsius. And we conducted an activation and graphitization technique at relatively low temperature with aid of metal catalyst and potassium hydroxide to obtain porous graphitic material. And the second step, the obtained porous graphitic carbon applied as anode of lithium battery. Through this detailed procedure, electrode slurry were prepared by mixing of the carbon sample as active material with polyvinyl fluoride binder and conductive agent. Then the powder mixture was dispersed in the solvent and cased on a copper foil using a standard Dr. blade technique. And the prototype of lithium-ion battery in coin cell were assembled in the half cell configuration using lithium metal electrode as reference and counter electrode. And we also use standard electrolyte lithium hexafluorophosphate as an electrolyte. And we also conducted the structural analysis with Raman. The obtained porous graphitic material were characterized using Raman and compared with the untreated sample and commercial graphite powder. As can be seen that nickel QH treated sample exhibit 3 peaks, D-band and G-band, D-band, G-band, and 2D-band. This spectra is similar to the commercial graphite, and the appearance of the G band, which is higher than D band, and also the appearance of 2D band are typical characteristic for graphite material. On the other hand, the untreated sample just consists of two broad overlapping peaks of D band and G band, showing the presence of amorphous carbon structure. In addition, the quantitative analysis based on the integral area ratio of the G band and D band, or we call it with Ig per ID. The calculated Ig per ID of the nickel QH treated sample appear much higher than untreated sample and close to commercial graphite. And it revealed that succeeded in converting coconut fiber into graphitic material. And furthermore, we also characterize the sample with the XRD. This is the XRD pattern. XRD pattern of untreated sample display two broad peaks at 2 theta value of 33 and 43 degree, respectively, indicating the predominantly amorphous phase. This result demonstrates that pyrolysis process at this temperature without any treatment cannot convert the structure of the biomass waste carbon into graphitic. While for nickel QH treated sample exhibit a much sharper and stronger 002 peak, followed by decrease in the interlayer spacing to around 1.33 nanometer compared to untreated sample and closer to the peak value of the commercial graphite. This result also revealed that our sample nickel QH treatment has converted the amorphous structure of biomass waste carbon into graphitic. This finding is consistent with the Raman. And we also conduct TEM in conjunction with selected area electron diffraction pattern or site in depth observation and structural ordering of the sample in conformity with the finding of XRD and Raman. The TEM image of untreated sample reveal disordered microstructure or randomly oriented structure, which is characteristic of amorphous material, and the appearance of the diffuse ring in the side pattern also confirm the amorphous phase in the untreated sample. On the other hand, the presence of graphitic structure in the nickel QH sample are clearly visible on the TEM image. Graphitic region are seen as ribbon-like structure in the low magnification, and on the higher TEM observation, focus on this ribbon-like structure reveal well-defined lattice fringe in this nickel QH treated sample. The graphitic region are composed of multi-layer graphene sheets spread by interlayer distance about 1.32 nanometer. Hence, the spot pattern observed in the side image for nickel QH treated sample confirm the existence of crystalline ordering or graphitic structure. And we also analyze the pore structure using the ET method. This is nitrogen absorption desorption isotherm graph of nickel QH treated sample, display a hysteresis loop and belong to category of combined type 1 and type 4 isotherm according to the IUPAC classification. This suggests that nickel QH treated sample contain a considerable number of micropore and mesopore texture. This was verified by the pore size distribution curve derived from the nitrogen absorption isotherm. The nickel QH sample show much higher surface area compared to the untreated sample and the commercial product of graphite powder. And this data analysis proved that nickel QH treatment succeeded to convert the coconut fiber or from biomass waste into porous graphitic carbon material with high graphitization degree and surface area. And we also analyze the battery testing, the battery performance. We characterize the performance as anode of lithium-ion battery using galvanostatic charge discharge and cyclic voltammetric tests. The CV curve of the untreated sample is typical CV curve of amorphous carbon. You can see that in this image. Meanwhile, the CV profile of nickel QH treated sample record in the first trip cycle show a redox peak similar to the commercial graphite, and these are the first 3 cycle of charge discharge profile of all sample tests at current density of 0.05 C. It can be noticed that there are differences in the shape of the CD curve in each carbon sample, indicating the differences in the lithium-ion storage mechanism. The untreated sample display a sloping profile with a specific capacity up to 75, around 75.20 milliampere hour per gram. The sloping profile indicates that lithium-ion are dominantly stored at the surface of micropore defect and its side, and the low specific capacitance of the untreated sample due to its amorphous structure and low surface area. Meanwhile, for the nickel QH treated sample exhibit a CD curve with a low voltage plateau profile at lower than 0.25 volt, and at high voltage sloping profile substantially identical to commercial graphite. This profile show that the ion storage mechanism of both sample is dominated by ion diffusion in the graphitic interlayer, which is comparable to the storage mechanism of commercial graphite as result of the existence of graphitic structure in the sample. And the sample also show the higher specific capacity, about 300, almost 400 milliampere hour per gram, even exceeding that of commercial graphite. We just have about 339 or 340 milliampere per gram for commercial graphite powder, which can be attributed to the high degree of graphitic structure and surface area. And this is also differential capacity curve dq per dV of the lithiation process, which are used to gain further insight about the ion storage mechanism of its sample. Okay, we also conducted the performance at increasing rate from 0.05 to 1 C, and cycling stability at a constant rate of 0.5 C were also performed. The specific capacity of all sample declined as the current density increased. Then when the current density is restored to 0.05 C, the specific capacity of each sample almost recovered to its initial specific capacity at 0.05 C, demonstrating that the material exhibit excellent rate performance. Furthermore, the cycling performance of all sample at constant rate of 0.5 C were almost performed. It can be seen that porous graphitic carbon electrode prepared from coconut fiber demonstrated better cycling performance after 30 cycles compared to commercial graphite. And we also use a lithium-ion battery coin cell from coconut fiber anode to power the LED light, and it worked perfectly. Okay, this project is collaboration research between National Research and Innovation Agency and Queen Mary University of London. This is our members of team. We have a UK partner, Miss Eva from Queen Mary University of London, with this as her responsibility in this project. And we also have a member from the battery research group in our institution, Ms. Kristen and Slamet Priyono, Mr. Slamet Priyono, who have a responsibility in assembly and characterize the battery performance. Okay, this is our conclusion. we have succeeded in converting the unused Indonesian biomass waste from amorphous structure into graphitic carbon at low temperature of around 1,200 degrees Celsius and apply it as anode material, as sustainable anode material of lithium-ion battery. And our anode, material also pose high graphitization degree that is comparable to commercial graphite and produce a higher specific capacity compared to commercial graphite anode. And this is our research impact to reduce the CO2 emission from burning and decaying the agriculture waste, as well as the use of less fuel and lower temperature during the graphitization process compared to commercial graphite production. And then improve the economic value of function of waste, or in this case, biomass waste from Indonesia, and also contribute to the gradual curbing of climate change related effect by helping to create battery for CO2 emission free vehicle. And I want also remind you to be wise with your waste, start to sort your trash, and support to save the earth. Okay, I think it's all from me. I will give back the time and screen to the Mr. Dinan. Thank you, Mr. Dinan.
Thank you so much to Ms. Dina, and of course to all speakers for giving us insightful knowledge in today's webinar. So now it's time for a Q&A session. Participants are allowed to ask questions either in English or in Bahasa Indonesia. And I invite all of you who want to ask directly, please use the raise hand feature on your Zoom.
I ask first question to all the speakers, three speakers. It's okay?
Yes. Yes.
Okay. So, Miss, are you still here?
Yes, Prof.
Okay. So you did. You went to 3 different places, yes? Are you, yes?
Yes.
In Japan and Neutron from Kamiyama group, and then you moved to the other group and Node postdoctoral. Okay. So your main is that the developed finally for the solid state battery, right?
Yes.
Okay. So have you made it, have you fabricate the product of
No,
your battery?
Actually, for hydride ion, actually, we started, not really, but we already started to find the electrodes, the suitable electrodes. I think in the near future, the paper will publish from our group. We already found the best combination for the solid state battery for hydride ion. But I think for me, because I think I want to continue my research in Indonesia, I have planned to return to Indonesia, and actually I start to consider the lithium air battery. So I will start research of lithium air battery and focus on the cathode and assembly the solid state battery, but now not yet.
Okay. So so it means that you produce and you characterize the solid electrolyte, yes?
Yes.
And in the current stage, yes, right? Because you still find out what is the combination of the cathode and anode, right?
Yes. Right.
Okay. So I hope that it will when you come back to Indonesia, it will be also a challenging to start with the solid state battery. Yeah. So far, maybe there is a group in UNS that I don't know does also the solid state battery. Well, formally also we made it, yes, with the thin film battery, but the prospects is quite good. Okay, so your plan to come back to Indonesia, yeah? So welcome back. Okay, we discuss later. Okay, yeah. Yeah, well, you should contribute for Indonesia at least, yeah. Welcome also want to join with the NBRI. Okay, so the next question I want to give to Mas Dimas.
Yes,
Okay,
Prof.
so I saw that from your papers, several papers with as Islam. Is that Saiful Islam, the one from Bath from UK?
Oh, no, Prof.
No?
It's in my group.
Oh, different. Because there's a famous scientist
Yeah,
in
yeah,
UK,
right.
right? You know,
Yeah,
as
yeah, I
Islam
know,
also. So I was wondering because you're working in Korea, but the paper is. I thought this guy also, yeah.
Yeah,
Because he does also the solid state battery. So from your work, you made already, you fabricated already the battery using zinc is ions.
Yes, Prof. Yeah, we made for pot cell for this zinc-ion battery.
So that the zinc ion battery, what is the combination? The anode and for the anode cathode, and what is the arrangement?
Okay. So in our lab we use half cell, Prof. So usually we use manganese oxide or vanadium oxide for the this zinc-ion battery for the cathode material, and then we use the electrolyte like liquid electrolyte, or in my case we use the gel electrolyte using zinc sulfate and mix with in the DI water, the water-based solution. Then the anode usually just zinc metal plate, the zinc film, or we also can use for the carbon paper as the anode for full cell.
Okay, so
it just works same like
so at first you make the half cell, yeah, but using
Yes.
zinc plate, yeah, instead
Yes.
of lithium, because the ion move this the zinc, yeah.
Yes,
Is that
correct.
right? Yeah.
Yes.
And for IU, the ion move is the hydrogen, yeah.
Yes.
Right. Okay. So it's different. That's very interesting. Okay. One more question for Dimas. It's how about the prospect for developing this manufacturing this in Indonesia?
Oh yeah, actually in Indonesia, for the manufacturing process, I'm not sure about this zinc and battery, Prof, because usually people just do for the lithium and sodium. For the recent progress, the new material is new battery is sodium ion battery, but that not many people do zinc ion battery. And I think if some lab or some, I don't know, manufacturing company making the lithium-ion battery, we can also make a line there for the zinc-ion battery because it's just similar process, Prof. So they are not much different, just different in the materials for the electrolyte, and then cathode and anode almost similar. And yeah, we can replace the lithium-ion battery production line and make another line to make this zinc-ion battery if it's possible.
Okay. Okay. Thank you, Dimas. Okay. So my last question to Fredina. So have you made the patent for your product?
Yes, Prof, under drafting process.
Drafting process. Yeah,
Yes.
that's good. Yeah. Okay. Have you thought how you scale up this? You know, the thing is the problem with us is stop with the prototype, and then scaling up just different matter. But if you want to produce, I think, in NBRI we produce now the pilot plant for cathode, yes. But I wish that if you can produce your carbon, we will scale up, yeah, scaling up. That is very, very good. So we can do the combination, both the graphite from local resources. How do you think about that?
Okay, Prof. Actually, the temperature of this process in this proposal or in this project is quite high. In this case, we use at 1,200 degrees Celsius. So we have to reduce the temperature, so we can use the other furnace, chop furnace with bigger, bigger capacity to produce a bigger graphitic material. So in my next project in Rumah program in BRIN, I introduced to reduce the temperature up to 800 degrees Celsius to produce this porous graphitic carbon material and apply as anodes of lithium-ion battery. And let's see how the performance in the half cell. If it's good, so I'm confident to apply it in the bigger dimension, maybe Prof, in pound cell or in cylinder cell.
Okay, so no, you are trying to reduce, yes, to reduce the temperature.
Yes.
Okay, but we will wait for your product,
okay.
and then because I think it should be also not only the cathode, the anode should be from the local. Yeah, if you have some material, so we can make the cylinder.
Okay.
Yeah, we can discuss later. Okay, thank you, Dinan. Yeah, good luck for everybody. Yeah, thank you for your having this. I think you're great. You are great scientist, young scientist, millennial, and you will take over for the future generation in Indonesia. Okay, and NBRI we always will support. Okay, thank you.
Thank you.
Thank you, Prof.
Thank you, Prof. Evie, for the question, and thank you to all speakers also for the answer. Maybe I will ask again to all participants, if you have any question, you can ask via raise hand or via chat box. If there's nothing, maybe I have a question to Mr. Dimas. How about the prospect for zinc-ion battery in terms of specific energy compared to lithium-ion battery? As we know that lithium-ion battery has limitation until now. Okay, that's my question.
Yeah, it's very good question. Yeah, because the energy density of the zinc-ion battery is still less compared with the lithium-ion battery. That's why we want to this for diversification. So we are not going to use this zinc-ion battery for electric car or mobile phone and laptop because it's gonna be very weight. The weight is compared with the lithium, maybe it can be 2 times. And then the voltage also, the voltage is 50% less than lithium-ion battery. So because the hydrogen evolution for this zinc-ion battery system, it can reach only maximum 2 volt or 2.2 volts. Compared with the lithium, it can reach until 4 and 5 volts for the application to turn on your phone or another like LED. So when we use for turn on the LED, actually, for the lithium we only use one coin cell, but for the zinc-ion battery we need about 2 or 3 cells. That's why we use this battery to replace the lithium battery to make the energy storage system for smart grid. So it should be like just static application. So we're not gonna move the battery to another place, just stay there. That's why we developed this as smart grid for renewable energy. We can see the renewable energy is very good for the environment and then for the human life, but when it comes to energy storage with lithium-ion battery, it's just like similar. It's dangerous for environment and then it can explode. That's why the zinc-ion battery can solve the problem to make more low cost. It can give low cost production and then very safe. But for the specific energy and then the voltage range or energy density, lithium-ion battery still cannot compete with this. I mean, zinc ion battery cannot compete with the lithium ion battery. That's why just diversification solution. Thank you.
Thank you so much for the explanation. Maybe my last question to Ms. Redina. I just found that the result from your biomass web showed that the specific area for around 100 meter square per gram, and it's pretty higher than commercial graphite. Is that an effect from this result? Thank you.
Yes. Okay. According to the previous paper from other researcher, that porous structure is also need to improve the capacity of lithium-ion battery due to lithium ion can store in the porous structure, in the micropore, mesopore, and also in the defect structure, not only in the interlayer graphitic. So it is the reason why I try to produce the not only graphitic structure, but also porous graphitic structure to improve the performance of lithium-ion battery.
Okay, thank you. As we know, the large specific area not always what to say selalu lebih tinggi gitu. Not large specific area is not always produce specific capacity, right?
Yeah. So we have to find the optimum value among the porous structure and the graphitic structure. Yeah.
Okay, maybe that's all from me. If we have
maybe one comment for Mr. Dimas. Mr.
Okay.
Dimas, thank you. Mr. Dimas, I catch information from your slide that you need also carbon paper for make the full cell of zinc ion battery, right? Maybe I can support it because my material also, now I'm developing also apply the porous graphitic structure, the porous graphitic material into the carbon paper. And we have successful to make a carbon paper using the hydrophobic polymer to replace the commercial carbon paper from Toray product. If you're interested, I will send you our sample to test in your cell.
Yeah, because in our lab now we are developing the anode materials using surface modification. So we coat with PEG in the electrolyte and then deposit to the zinc metal as the anode. Because the zinc dendrite problem is always happen in this battery. Also in lithium, also there is like dendrite problem, right? Dendrite growth to the electrode, and it can make short circuit and catch fire. That's why, for the anode we are doing, and then for me itself, I'm doing the experiment with the zinc deposition to stop the dendrite growth. And you can send the sample and then let's try in our system here.
Okay, thank you.
Thank you.
Great, I think it's good. Collaboration.
Okay, maybe I will ask again the participants if there are any questions. Okay, to Mr. Subhan, please unmute and ask your question.
Oke, pakai bahasa Indonesia aja ya.
Iya, Pak.
Karena semuanya Indonesia kok gitu. Oke, terima kasih kesempatannya. Mungkin Dimas masih ingat saya kali ya.
Oh, Pak Subhan, LIPI Fisika, Pak?
Ya, sudah tidak ada LIPI, Pak. Tapi,
salam Pak Subhan. Wah,
ya.
Terima kasih sekali nih buat Pak Subhan dulu membantu saya membuat sel baterainya di LIPI Fisika sehingga saya bisa lulus sarjana. Terima kasih sekali, Pak.
Buat baterai pokoknya.
Baterai.
Saya mau nanya Dimas ya.
Oke,
dalam
Pak.
sistem baterai zinc yang dikerjakan itu sistemnya dia itu sebagai interkalasi atau sebagai alloying di sana?
Interkalasi Pak. Jadi ada zinc ion di situ yang berpindah dari positif, dari elektrolit ke katodnya terus keluar lagi gitu, sama kayak lithium Pak. Begitu.
Tidak alloying ya?
Bukan Pak, bukan
Oke,
alloy.
gitu. Oke. Jadi tidak ada apa lapisan yang terbentuk cukup tebal. Artinya dia bisa jaraknya lebih dekat ya, seperti lithium.
Betul Pak, iya.
Misalnya baterai aki itu kan, karena dia alloying, makanya jaraknya nggak bisa deket tuh. Karena juga water. Dia
Iya.
ada lapisan yang selalu terbentuk walaupun bisa berubah lagi ya.
Betul Pak.
Kalau memakai itu kan artinya berbasis water ya. Kalau yang berbasis organik sudah pernah dicoba belum?
Elektrolitnya Pak?
Betul.
Kalau berbasis organik ada Pak. Cuma ini ya Pak, karena zinc ion battery di lab kami ingin harganya murah dan tidak berbahaya untuk lingkungan, jadi kami membuat sendiri elektrolitnya gitu. Tapi beberapa paper melakukan itu Pak, ya hasilnya ada yang lebih bagus. Tapi kami tidak melakukan di sini untuk organic electrolyte. Jadi kami bikin sendiri water base pakai zinc sulfate, or manganese sulfate atau zinc triplate, gitu Pak.
Zinc chloride pernah juga coba?
Zinc chloride pernah Pak, tapi nggak bagus Pak.
Itu? Oh nggak bagus. Yang bagus apa?
Sulfate base Pak, zinc sulfate, manganese sulfate, sama triflate. Saya menggunakan triflate untuk menaikkan voltage-nya Pak. Karena kan zinc itu rendah sekali voltage-nya. Nah, satu-satunya jalan pakai zinc triflate. Itu agak mahal memang materialnya, tapi itu bisa menaikkan sampai 0,3-0,4 voltage range.
Berapa tegangan kerjanya itu?
Tegangannya umumnya Pak, itu 1,2 volt untuk sulfate base. Tapi di zinc triflate kita bisa naikin sampai 1,5-1,6 Pak.
Nah, kalau pakai yang organik itu bisa lebih tinggi tuh.
Betul Pak.
Bisa di atas gitu.
Nah, tapi karena organik ini apa?
Mahal ya?
Ya, jadi nggak ada bedanya nanti sama lithium gitu Pak. Kami mau bikin yang beda gitu sama lithium. Makanya quotes electrolyte gitu. Kayak karena kan zinc ini nggak butuh dirakit di dalam glove box. Nah, kalau pakai organik kita harus masukin ke glove box lagi Pak gitu.
Cyclability yang pernah dicoba berapa banyak itu?
Itu bisa sampai 2000 cycle Pak.
2000 cycle? Lama ya?
Betul. Itu high current.
High current ya. Jadi berapa C kalau itunya?
C-nya itu 3C, masalah apa ya?
Kok bisa 3C cepet ya?
Tuh.
Ya oke, good luck, bagus ya ininya, hasilnya ya.
Betul.
Satu lagi kalau Ibu Fredina boleh nanya.
Silahkan Pak.
Oh boleh ya. Ini Din, saya tertarik dengan hasilnya sudah sangat bagus ya, sudah menyamai dengan ternyata dengan grafik komersial gitu ya. Ya hebat lah.
Terima kasih Pak.
Saya mau nanya sedikit aja terkait dengan tadi ada yang belum ditampilkan terkait dengan shape-nya ya Din ya. Shape partikelnya gitu. Kira-kira bentuknya udah sama belum dengan grafik komersial gitu yang rounded misalnya. Kan itu penting juga.
Morfologinya maksudnya ya Pak ya?
SEM-nya ada nggak itu?
SEM-nya sebetulnya ada.
Komersial dengan produce gitu.
Ya, kalau secara analisis morfologi via SEM memang agak berbeda karena material saya dari biomass base yang memang sangat potensial sekali membentuk pori. Jadi kalau di SEM dia akan kebentuk kelihatan pori-porinya gitu. Kalau yang graphite kan dia bulk gitu ya Pak ya. Makanya surface area-nya juga kecil. Jadi kalau dia dari morfologinya sangat beda sekali Pak.
Oke. Kira-kira berapa partikelnya tuh rata-rata ukurannya?
Ukuran partikel.
Kalau baterai itu harus 400 mesh ya?
Ya, kita juga nge-mesh sekitar 400 mesh juga Pak. Karena memang sudah pernah kita mesh lebih kasar, memang performanya jelek, jadi kita coba diperhalus dan hasilnya juga improve ternyata.
Iya. Oke. Ya nanti kapan-kapan saya pengen lihat SEM-nya. kalau
Siap,
boleh.
Pak. Boleh Pak. Kebetulan Prof. Evi mau menginfokan manuskrip yang kemarin kita submit tadi pagi sudah dapat informasi sudah accepted gitu.
Oh, good. Congratulations. Q1 ya.
Thank you. Q1.
Wah, itu nanti Esti kabarin ke Prof. Alan. Ya, will inform ya to ya also to British Council.
Oke, Prof.
Yeah, great. Send me the file, yes? Yeah, the preprint.
Oke, Prof.
Selamat, Tin. Itu aja udah pertanyaan dari saya. Terima kasih.
Pak. Sama-sama, Pak.
Mr. Subhan. Hi.
Saya
Yeah, I think Subhan who asked. Pak Subhan, so maybe if Fredina still have some material for the EndNote, so Pak Subhan, can you make the full cell but with coin cell, yeah, full cell with coin cell, yeah, but if enough we make the full cell using our NMC product, yes?
Yes, possible, Prof.
Yeah, so we should try that, yeah? Okay.
Yeah, please welcome.
Okay, thank you.
Thank you to Mr. Subhan for the question. Maybe we come to the end of this session. Thank you to all speakers and participants for your kindly attention and participation. It has been my pleasure to be a moderator for today's webinar. Now it's time for me to return this session to the MC. Thank you.
Okay, thank you so much for the moderators and also for the speakers. We already learned a lot about today from our expert speakers. It is an honor to be here and have a discussions. But before we end up these sessions, I would like to invite our founder, Professor Dr. Renat Evi Kartini, to give a token of appreciations to our
Okay.
Also moderators.
Okay, thank you. Thank you, Sinta. Thank you, Dinan. You already lead this discussion. So first, I would like to give the appreciation to Dr. Nur Ika Puji Ayu ST, yes, from Tokyo Institute of Technology. So it's a great pleasure to have you. And then for me, it's, you know, I see you like my, yeah, you were great when you were my student. I think, and I was so pleased to see you grow up and then become a PhD. This is the first time I see you directly. Okay, so it's great. Yeah, welcome back, and then we wait for you to bring up Indonesia. Yeah, to build Indonesia, become a strong country. Yeah. So good luck, and then send my regard to Professor Kamiyama and also Professor Ryoji Kano. Yeah, right. So I hope you can also attend our international conference. Maybe I can invite him to our conference. Okay. Yeah, great. Yeah. Good luck, Ayu. Okay. So the next, I would like to give the appreciation to Mas Dimas. Yeah. Mas Dimas Yunianto Putro, ST MBA, sooner become PhD. I think you you also a great young scientist. So I met you in the international conference, and actually at that time also one of the president of the Material Society in Singapore also asked about you. You know?
Yeah. Yeah. Yes.
But you finish first, yeah. I think yeah. Some opportunity also to have the collaboration, yeah, right, yeah, in the so Professor Chaudhary, yeah, okay, no team might become the president of the MRI Singapore. Okay, thank you again. So good luck, yes, and then yeah, we hope that we can still have the contribution for Indonesia, okay, and then yeah, in the near future. Yeah, don't forget to come back. Okay,
Okay, bro. Yes.
Okay, for the next speaker, Fredina. Yeah, as I always said, you also really have you are really young, also talented scientist. Yeah, researcher, I think I saw you have so many patents, really great, yeah. And then a publication, and then also congratulations, you have already just published the journal from your last grant. I think this is one example of a good product, yeah, a good product. Please continue, yeah, in this field until you can make a factory, I think, of the anode in Indonesia. Thank you, Fredina.
Thank you, Prof.
Okay. Well, I should give also for the moderator. Sinta, no moderator does not have the certificate.
There is, Prof. Please wait a minute.
Okay. Okay, just give that. Okay, finally, I'm very pleased to have you, Dinan. Yes, you just 1 month in NBRI, so you did really well. Yeah, you work also hard. Yeah, making the carbon from rice husk. Yeah, I hope you good luck. Yeah, to have it, and then you can collaborate later on with the others. Yes. Yeah, here with Fredina, with Mas Dimas, and then also with Bayu, yeah, for the future. And then I hope also you will succeed. Yeah. Okay. Good luck.
Thank you, Prof, for this opportunity.
Okay. Okay, Sinta.
Okay, thank you so much, Prof. Evi, for your time to deliver the token of appreciation for our speakers and also moderator. But before we comes up with the closing sessions, please allow me to give us some announcement from the NBRI. Okay, so as Prof. Evi mentioned earlier, that NBRI will have a next agenda, which is a huge event of the NBRI and also an annual event of the NBRI, which is an international conference on batteries for renewable energy and electric vehicles in June 2022, from the 21st until 23rd of June 2022. So this event invited for the professor all around the world and also have a very various plans. So please make sure you are registered to these events, because this is going to be a very interesting event. And followed with the ICBRF 2022, we also have a Youth Ideas competitions, which is a paper and microblog for a student and young scientists in Indonesia. So for the information, please visit our website on www.n-bri.org, and then you will find the event of ICBRF 2022 and also your idea competitions 2022. So this is the announcement, and now it comes up with the closing sessions from Professor Dr. Renat Evi Kartini. Prof. Evi, the time is yours.
Okay, thank you, Sinta. So finally, on behalf of the National Battery Research Institute and also on behalf of Professor Alan Drew, yeah, he could not attend this event because of the different time zone, yeah, 6 hours behind, yeah, so still early morning. So thank to all the speakers for attending this, for giving and sharing the lecture and experience in this Millennial Talks, and also for all the participants who came to participate in this Millennial Talk for today. At last but not least, I would like to thank also for the PIC of this program, Dinan, and also Sinta, and also all the NBRI team. So we look forward for all the collaboration for all of us, the millennials, and then all the students. Yeah, welcome to join the NBRI internship or collaboration or research program. So I hope that all of you success in your study or research. Once again, thank you to all of you.
Okay, thank you so much, Prof. Evi, for the closing sessions. So with these closing sessions, our event is already finished. Thank you so much for all the speakers, moderators, and also participants for attending this event. And then please kindly...
You have a photo session.
Oh, yeah.
Ah, you
So-
missed that.
Yes, so to all the participants, kindly turn on the video. We'll take a pictures
You missed that
together.
already. Yeah, it's okay.
All right. So the computer can help me, and we're gonna take a pictures in 3, 2, 1. All right, thank you so much. So before we end up the session, please make sure that all of you already followed the social media of the NBRI on Instagram, nbri.indonesia, and also on LinkedIn, National Battery Research Institute. And we also have a YouTube channel where you can rewatch about our previous event in National Battery Research Institute of Indonesia. So please make sure you already register also as a member of the NBRI throughout our website. And I also would like to remind all of the participants to get the certificate. Please kindly fill out the attendance form. And the committee, could you please reshare the attendance form on the screen? And also, you can check the link on the chat box, bit.ly/attend-mt3. So that's all from me. Thank you so much, and stay healthy and stay safe. Have a nice day, everyone.
And you too. Thank you. See you.
Yes,
you.
thank you.
Yeah.
Thank you, Prof.
Ya, thank you ya, Dimas,
Oh,
Ayu, Redina, semuanya. Ya,
Thank you,
See you
Prof.
soon.
ya. Kangen juga Ayu nih. Ya.
Thank you.
Kamu tambah cantik ya di Jepang nih. Udah kayak orang Jepang. Saya kira lupa bahasa Jawa nanti.
Yeah, actually, I can speak Japanese a little bit.
Oh, really? Oh, great. Yeah. You speak Japanese very well, yeah? Also writtenly, okay?
I usually for work, I do all in Japanese.
Oh, really? Oh, it's great, great. Yeah. So you have been there for 5 years?
Yeah, this is my 6 years.
Your 5 years, yes?
This is 6 years.
Oh, 6 years. Ah, yeah, don't forget to come back, okay? Yeah, so it's a long time ago. So yeah, we'll discuss later about this opportunity. Okay, Ayu, yeah? Keep healthy there. Okay, thank you.
Much.